Hello. Let's start lecture number 6, which is the second part of linear algebra. As I promised you last time, I will talk about the relationship between the things we are talking about right now and the things you have learned in high school. Okay, that's here. Okay, let's start talking about from a norm of the vector. You have learned that the vectors do have the size, the length, and the direction. And that's this one here. In the university, made a mistake here. Okay. In the university, we call the length of the vector as norm. Norm is a word we use for the size of the vector. Okay? And for the 2D vector, this is something we have learned. Here, this notation here, this is a vector, so it's supposed to be single column, but using transpose to make it a row vector. So that's how I save the space. Okay, here's one more time. You can generalize this one into 3-dimensional space. You add one more, v3 squared, and then v4 squared, blah, 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 and goes up to vn squared for the n-dimensional vector. Once again, I have used this notation to make it, to conserve the space here. So, norm versus inner product. If you look at this one here, if you do remember the inner product we have learned last time, inner product was you multiply the first element of the first vector to the first element of the second vector, blah, blah, blah. And if you multiply v to itself, what's going to happen is that those two elements are the same, so v1 squared, then v2 squared. So this here, inside of the square root is actually the inner product of itself. Right? So that will give you the square of this one here. So if you take the square root of this one here, that will become the norm, the length of the vector. So what does it say? This is a very special inner product, right? You are multiplying, you're taking the inner product of itself. Of course, you can take inner product of many different vectors, but so this is a very special case, will give you the norm. So, inner product and norm is a very special case. That means, what does it say is that we can define the norm by inner product, using product. If you have inner product, then you can define the norm by square root of inner product of itself. So, inner product is a much broader concept. That is the reason why inner product is more useful for us. Okay, vectors in 2D place. And so, let's look at this one here. All right, and let's look at some of the things we have done last time in terms of geometry. Okay, geometry, V1, V2, meaning the V1 x-axis, V2 y-axis here. And the first thing we have learned was to multiply, before that, the length and the direction, yeah, right. Well, the length here is the square plus square root. That's something we know already. And theta, the angle here, is used for the direction of the vector, right? And arctangent is used nicely here. V2 over V1. That's tangent. So therefore, arctangent of that must be the angle there. Okay. So this was the one I was going to talk about. Scalar multiplication, what's going to happen? If you multiply 2, what we do is we multiply each element to 2 here. So you have 2v1 here and 2v2 here. And the vector becomes this one. How about the angle? You have, instead of v2, you have 2v2, and instead of v1, you have 2v1. So 2v2, 2v1 and of course 2 cancels out. So that's exactly the same, meaning that multiplying a scalar does not change theta. So direction is not changed. Scalar multiplication, Scalar multiplication does not change the direction. Okay, that's well understandable, I guess. That only changes the length. Okay. How about addition? After the scalar multiplication, we talked about the addition, right, of 2 vectors. So you add them. Probably this is how you learned it. You shift this vector to the tip of another vector and find the resulting vector. That is going to be the addition, right? So this one plus that one is this. Easy to draw it. How about subtraction? Well, the catch is this is V plus minus W. So draw minus W and add them together. So for this W, this is minus W. So you shift this one to the tip of that and that. So this becomes U minus V. And or you can look at this one here, this and that are parallel to each other. So, and minus W is this one here. If you shift this way, that is a way. But if you shift this vector to this one here, because of the minus, direction is changed from here to there. So that's going to be minus, right? Well, that's probably how you learned the additions and subtractions in high school. But anyway, so you can use any of those geometry to compute the, to visualize, I should say, the additions and subtractions. How about inner product? Aha, this is a thing quite different from high school. I am sure you have learned the inner product by this formula here. Inner product is given by the product of the length of the first vector and the length of the second vector, and the cosine of this is the angle in between those 2 vectors. And I will show that this definition is exactly the same as the definition, element-wise addition, multiplication, and add them together by using this one here, the cosine formula. This is again something you will learn in high school. So I will use this formula. For a triangle, general triangle, if you have theta which is against C here, C squared is equal to A squared plus B squared minus 2AB cosine theta. That's something you have learned. So from this equation, you can say that AB cosine theta is equal to 1/2 of this squared plus squared minus C squared. Okay? And remember the last slide where we have this type of triangle and like this. If you have W vector and V vector here, that vector is V minus W, right? So if you look at this, if you call this W vector, then the B is the length of W. A is the length of V, C is the length of this one here. So that equation here, using this, could be written in this form. AB cosine theta, this times that times cosine theta. That's that. Is equal to 1/2 of this squared minus this squared. So what do? You just compute them. Okay, V norm squared is V1 squared plus V2 squared. W norm squared is W1 plus W2 squared. And this minus part, that's element-wise subtraction multiplied together. Okay. compute them out. Here, v1 squared will be cancelled out, v2 squared will be cancelled out, w1 squared, w2 squared cancelled out. So the only terms remaining here are the cross terms here, and the minus sign and the minus sign will cancel them out. So 1/2 of this, twice as much of v1 w1 plus twice as much of v2 w2, and 2 cancels out. So this is what you got. Of course, that is our definition of the inner product. So therefore, the inner product you have learned in high school is exactly the same, identical to the inner product we have introduced here. So you can use it, you can use them interchangeably. But this, I would say this one is very interesting, or you can find something very interesting out of this formula here. Suppose theta is equal to pi over 2, 90 degrees. Then what's going to happen? Well, of course, the cosine is 0. So that means the inner product becomes 0. Okay? So if the angle between two vectors is 90 degrees, then inner product is equal to 0. Okay? This can be used to find out, see if two vectors are perpendicular to each other, 90 degrees or not. You compute the inner product using those element-wise computation, and if it becomes 0, then those two vectors are perpendicular to each other, orthogonal, 90 degrees, 1/2 pi, whatever you call, okay? So you can use that to check to see if those two vectors are perpendicular to each other. So this is a nice definition here for that. Okay. Because matrices have lots of elements and can be used for many purposes, there are many particular, special matrices. So let me introduce some of those matrices. One of them, the first one is a square matrix. Number of rows and number of columns the same, square. Well, understandably, it's square, right? Number of rows, number of columns are same. That's n by n here. The next one is a type of square matrix where transpose is equal to itself. Even if you change the rows and columns here, you get exactly the same thing. So it has to be a square matrix, of course, but this is another property. Okay. 3, diagonal matrix. Only diagonal elements equals 0 in symmetric matrix. This is symmetric, right? And only diagonal elements are non-zero. So this is an example here. And this is identity matrix. Ooh, the example for the second one appears now. That's too late. But anyway, let's take a look at this one here. Identity matrix, you only have ones on diagonal. Everything else is equal to 0. It's a very simple matrix, but it's a very interesting matrix. We can use this. There are lots of interesting use for that. All right. Asymmetric matrix. Well, if you take the transpose, then it becomes minus A, or the minus of A transpose becomes original one. If you look at this one here, 3 minus 3, 5 minus 5, minus 1, and 1. If you flip it, plus and minus changes. So this is minus M transpose. So for a symmetric matrix, the diagonal element has to equal to 0, right? Plus and minus have to change. And there's only one number which is the same as its negative. That's 0. All right. Upper and lower triangular matrices. Upper triangle matrix. Upper triangle here, you have lots of numbers, but lower triangle is equal to 0. The other way around, lower triangular matrix, lower part, you can have any number, but the upper part is 0. Those matrices are handy when we solve some of those matrix equations on computers. So you will learn those in linear algebra class, not here. I'm just introducing those terminologies. How about determinant? Okay, when we deal with square matrices, this is one thing we just have to come up with. We just have to learn it. And another thing is the thing called the inverse matrix. But to learn inverse matrix, we do need determinants. However, the determinant comes from totally different idea. It is the existence check for unique solution. Unique solution for what? Well, let Ax is equal to B. So that's the equation here. That could be, well, 22 by 22. Many equations for many unknowns. N equations and N unknowns. So, before you start solving that equation, you'd like to find out, see if the solution, unique solution exists or not. Okay? So, a unique solution X exists if the determinant of the coefficient matrix here, this thing here, is non-zero. So that's what determines the existence of unique solution. That's why it is called a determinant. So the question is, how do we compute this determinant? But before going into that, let's look at a very solid case of 2 by 2. For a 2 by 2 equation here, this is equivalent to that, and which is equivalent to that. For that, you know how to solve. You know the solution could be written in this form. It's very easy to do it, right? Well, not always. Provided that this bottom, the denominator is not equal to 0. If that is equal to 0, both of them goes up to infinity, right? So you forget about that. So the solution, unique solution exists if this is not equal to 0. So comparing this statement and that statement here, can we say determinant A is equal to that? How do you think? Yes or no? The answer happens to be yes. Wow, great. For the 2 by 2 matrix, so this is correct. Determinant A is AD minus BC. So for 2 by 2 matrix, we do know the determinant. Okay. How about 3 by 3 or larger matrices? Can we do the same thing again? You solve that and find out the denominator? Well, of course you can do that, but for the 4 by 4, blah, 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 probably you don't want to do that. So what I do is to give you the answer for a general case and then explain. The determinant of a matrix n by n is given by this formula here. Wow, summation. It runs from 1 to n. So you have to add n of n numbers here. Each one of them, that's the element of the matrix. That's minus 1 to the I plus j power. So therefore, this is going to be 1 or negative 1, depending on I plus j is even number or odd number. And this one here, something which is new because this is large A, this is not a small a, so it is not an element of original matrix. This one here is smaller matrix called the ij minor of A. So this is the determinant of the ij minor of A. And J is free. Here, I runs from 1 to n, so we know what happens to I. But J, there's nothing. It's free. You can choose any one of them. 1, first column, 2, second column, or whichever the one you like. So that will give you the choice. Okay? But anyway, so what is this minor? But I have to explain that particular equation here with this one here. That's the fact is that A, starting from A, the determinant of this one, you need the determinant of that one. So therefore, what's happening here is that the determinant of this matrix n by n, you need the determinant of n minus 1 by n minus 1 matrix. Okay? So once again, how do you compute n minus 1, n minus determinant? You can apply the same theory again, use n minus 2, n minus 2 matrix. Aha! So you can repeat this one again and again and again, and eventually you come up to 2 by 2 matrix, for which we already know what the determinant is. So you can start from that, goes up or come down, whichever you like. But probably you can imagine how complicated or cumbersome to do this. All right. Besides, okay, what is this A minor? Okay. Definition: the ij minor of a matrix A is constructed by eliminating ith row and j's column from A. And this one here I call machine gun operation. Eliminate Well, if you look at the figure, it's easier to understand. So you have this n by n matrix A, and you have ith row and j's column, and get rid of those. Shoot them out. Then you come up with ij minor here, aij. Okay, that's how it goes. And definition: why? Why? This one here appeared in the equation for the determinant. Actually, this one has a name. This one here is called the ij cofactor, which is the determinant of minor times minus 1 to the i plus j power. Okay, this one here is called a minor. Okay, why? This one here we will use to define something useful. The adjugate matrix, matrix A, D, J, A of a matrix A is defined as that. Okay, so all of those probably is question mark and question mark for you. What the use for that? But before going into that, let me talk just one thing, that don't forget this transpose. Adjugate matrix do have transpose here. And that one, many of my students forget. So don't forget that. But anyway, crisscross operation, what is this? Blue add and orange subtract. Oh, 3 by 3. Seems to be we're talking about 3 by 3 matrix. Yes, determinant of 3 by 3 matrix. So let's compute this one here using 1, meaning that first column here. Okay, using that. So minus 1 divided AI1. So AI1, A11, 21, and A31. So 1, 1, first column and the first rows are eliminated. So this one here is A11 here is this one here. Now, similarly, A21 is this one, that. So write them down. You come up with this one here. That's first row and the third row. This one here, second and third, and the first and second row. Determinant. Okay. Now you have 2 by 2 determinants, so you can compute them and come up with this one here. Wow, you have 1, 2, 3, 4, 5, 6 terms. Well, you can put all of them together. You come up with this one here. 1, 1, 2, 2, 3, 3. 1, 2, 2, 3, 3, 1. 1, 3, 3, 2, 2, 1. Here, 1, 1, 3, 2, 2, 3. 1, 2, 2, 1, 3, 3. 1, 3, 2, 2, 3, 1. Is there any order, or is there any special characteristics? That's what this crisscross operation. If you look at this, those three terms, those are the elements on those three blue lines. You multiply all those elements on the same blue line, you come up with 1, 2, 3. And those three negative ones are on those orange lines. So you multiply all those elements and then subtract them. Will give you the determinant A for 3 by 3 matrix. So this is a crisscross operation. This is an operation you can use to compute the determinant of 3 by 3 matrix. So second order matrix, we do this exactly same thing, right? Well, A, B, C, D. Determinant was AD minus BC. So that's this one here, this is plus, this one here, that's minus, that's crisscross once again. So second order 2 by 2 matrix and 3 by 3 matrix, you can use pretty much similar operation to compute the determinant. 3 by 3 case, you have 3 and 3. 2 by 2 case, 1 and 1. That's it. So that's easy. 4 by 4, too bad we don't have a computation like this for 4 by 4. So up to 3 by 3, you can compute the determinant pretty easy. All right. Inverse matrix. What do you mean by inverse matrix? We talked about sines and cosines and etc. and inverse function. Goes the other way around, right? So inverse matrix once again goes the other way around. Namely, AX is equal to B. That's from B to find X, right? Instead of that, X is equal to A inverse times B. That's starting from, well, I'm sorry. This is, if you have X, you can compute AX and compute B. Here, if you have B, B and A inverse compute X. So it goes the other way around. That thing is actually the inverse matrix. And to define the inverse matrix, we use the one called the algebraic matrix. Wow, this is a place where algebraic matrix comes in, and the determinant. Okay. If the determinant is not equal to 0, if there is a unique solution, then the inverse A, inverse of matrix A is given by this one here, 1 over determinant of A times algebraic matrix A. And AX equal to B can be solved for X as this one here, the one I just wrote down here. And since X can be written in this form, X, there exists unique solution. For the existence of unique solution, A determinant has to be non-zero, therefore you can compute 1 over A determinant. Okay? So A inverse does exist when this is true. So to solve an equation like this one here, you only have to compute the inverse matrix. Okay, example, 2 by 2 matrix. Determinant is this one here, and algebraic matrix A happens to be this one here. You get rid of first and the first column and the first row, you get D, and the first row and second column you get C, and so that's minus C, and that's minus because this is 1, 1. That's even. 1, 2, odd. 2, 1, odd. 2, 2, even. So that's plus, minus, minus, plus. And if you get rid of the second row, second column, you get A. So that's algebraic matrix here. Okay? So, A inverse by this definition is this algebraic matrix times 1 over this one here. And show this. Aha! I already showed it for you. But anyway, do it. And that will give us the same solution as the one we had. Well, properties. There are lots of properties of matrices which you can use when you do the manipulation for the robotics control. First one is a trivial one, an obvious one, that A inverse times A or A times A inverse is identity matrix. Well, that is so. That's very easy to show. Like, if you multiply A inverse for this AX is equal to B from left-hand side, yeah. This one here is abbreviation of left-hand side. Left-hand side. And the other one is right-hand side, RHS. Left-hand side, and compare with this one here. If you multiply A inverse here and A inverse here, you get A inverse A times A, X is equal to A inverse B. Okay. So, compare that with this one here. You have A inverse times A. Well, try that. Try that. You'll see it. Try that. And for the second one, A inverse, you start from this one here and multiply A and compare with this one here. It's very simple. And use IA is equal to A for any A. Wow. So that's the position. You multiply, say, 1, 0, 0, 1, 2, A, B. This and that is equal to A, this and that is equal to B. Haha. So, identity matrix is called identity matrix. Not because of a choice. It is multiplied to any vector, goes back to the original vector, identity. That's why it is called identity matrix. Okay? Well, one other thing is that when we're talking about this determinant computation, we're talking about summation in terms of I, but you can exchange the roles of columns and rows. So here, the summation is in terms of J, columns, and I is free. The row is free. So you can choose any one of the column or row to compute this one here, to use this equation here. So choose it wisely. Choose it wisely. Like here. Suppose you're supposed to compute 2 to 6, 7, 0, minus 4, 4, 0, 5, or something like that. Suppose you are computing the determinant of this one here. I would use this. Why is that? Because you have to put the element here, right? So the first one is 2. Okay, and second one, 0. So that term will go away. Third one, once again, 0. So that term will go away. So if you use this column here, summation reduces to only single element. So choose whichever the one has many zeros in it. That is a catch. Choose the column or choose a row which has the largest number of zeros. That will give you the easy computation. Okay? Did you write that down? You better write that down. Okay. Coffee break 5. Strange facts for matrices. Matrices, you have many elements into it, so therefore interesting thing or a strange thing happens. If x squared is equal to 0 for a variable, of course we know that x is equal to 0. So what happens with a squared is equal to 0 for a matrix? Here, this one here is large theta. So that's a large, the capital letter for Greek theta. But anyway, that's a zero matrix. Nothing but zeros in it. So a squared for n by n matrix, a is equal to 0. Does it mean that a is equal to 0? Zero matrix? Not quite. Something strange happens. Suppose a is equal to 1, 1, negative 1, negative 1. Then a squared is equal to this one times that. 1 times 1 is equal to 1. 1 times minus 1 is minus 1. So add them together, becomes 0. Same thing happens everywhere. Okay. So a squared is equal to 0. But certainly a is not this one here. It's not equal to 0 matrix, right? So for a matrix, this, you have to be very careful. Of course, a is equal to 0 will make a squared is equal to 0, but there are other choices. There will be other choices as well. Okay, second one here, this is once again a very interesting property. Or if, well, let's take a look at 2 by 2 matrix only. Of course, I can generalize this one into 3 by 3 or n by n matrix. But anyway, if you have 2 by 2 matrix A, then there always exists two numbers, two scalars. That makes this one as a zero matrix. Linear combination, or I should say a squared plus alpha times a plus beta times I becomes 0. Let's try it. This is my favorite matrix. A is equal to 1, 2, 3, 4. That's an easy matrix here. And alpha beta is minus 4, minus 5. Then what's going to happen? If I compute this one here, a squared, alpha minus 4, beta minus 5. This one here, that's 4 times this. You can compute that one out, and you come up with 9, 8, 16, 17, minus 4 times this, and then minus 5, 0, 0, 0. And some like 9 minus 4 minus 5 is equal to, of course, 0. Right? 9 minus 4 minus 5 is equal to 0. All others, 16 minus 16, 8 minus 8, 17. Well, let me change the color of the pen. 17 minus 12 minus 5 is of course 0. Okay, so therefore this set becomes zero matrix here. So this is actually an application of the theorem, Carey-Hamilton theorem. But we will learn that and other interesting formulas in the linear algebra class. So wait until that time. So this is the end of this lecture on linear algebra. Next time I'll go into the most important part of this lecture, this class, which is differentiation. Thank you.